Hi everybody, this is Shiva Veeram signing. This is long time since I haven't taken any online sessions. So in this session I wanted to deal problems related to the Coulomb's law and electric field intensity. Already I have done one session related to this particular topic. Even there we have gone through a few number of problems also. In this session I wanted to focus on the problems related to the electric field intensity due to line charge and sheet charge. Let me continue the session. Here the first problem given to us is we are given a sheet of charge of rho s is equal to 2 nanocoulombs per square meter at the plane x is equal to 3 in the free space, and a line charge of rho l is equal to 20 nanocoulombs per meter located at x is equal to 1 and z is equal to 4, and we are asked to find out the magnitude of electric field intensity at the origin. Origin means 0, 0 and 0. And the direction of electric field intensity, the second one is we have to find out the direction of electric field intensity at 4, 5, 6. This is the point we are given in the space. And the last one is we need to find out the force per meter length on the line charge. So let us find out the solution for these three cases. First of all, let me draw the three axes x, y and z, and let us locate the line charge and the sheet of charge. First of all, I am drawing the three axes x, y and z. And this point corresponds to x is equal to 3, sheet of charge. The charge density is given as 2 nanocoulombs per square meter. This particular plane corresponds to the sheet of charge located at x is equal to 3, and this would be parallel to the YZ plane. The magnitude of the sheet of charge is given as 2 nanocoulombs per square meter. Next, the line charge is located at x is equal to 1 and z is equal to 4. I am locating the points x is equal to 1 here and z is equal to 4, and join those two points, you get the line charge located. In the given case, rho l is equal to 20 nanocoulombs per meter. So first we have to find out the electric field intensity. E bar at origin, that is 0, 0 and 0. Here the total electric field intensity at origin is the resultant of the two charges. One is due to the sheet of charge and another one is due to the line charge. So E bar due to the rho s, that is sheet of charge, plus E bar due to the line charge located at x is equal to 1 and z is equal to 4. Here Let us find out the E bar due to the sheet of charge and consider this as ES bar, and we know the formula for calculating ES bar is equal to rho S by 2 epsilon naught into AN bar. So here rho S is the charge density given in the problem. It has 2 nanocoulombs per square meter, and AN bar is the unit vector directed perpendicular to the surface. Here in this case, if you observe, AX bar minus AX bar is is considered as the unit vector towards the origin. So if it is considered away from the origin, it will be positive AX. As it is towards origin, it will be in the negative X direction, and it will be minus AX bar. And substitute the values, you get and if you cancel all these things, you get minus 113.09 AX bar. Next, let us find out the electric field intensity due to the line charge located at X is equal to 1 and Z is equal to 4, and consider this as EL bar. The formula for finding out this electric field intensity due to the line charge is equal to EL bar as equal to lambda divided by 2 pi epsilon naught into R into AR bar. So here R is the radial distance and AR is the unit vector directed towards the point where we have to find out the electric field intensity. So lambda is given as 20 nanocoulombs per meter, and R is the radial distance, and AR bar is the unit vector along R. First of all, let me write down the formula for finding out EL bar again. EL bar is equal to lambda by 2 pi epsilon naught into R into AR bar. So here R is equal to square root of, the point is here x1 and z coordinate is 4 and y is equal to, y will not be considered here because the line charge is going to be placed in the xz plane, hence the y coordinate will not be considered here, it will be 0. Hence the magnitude of R is equal to square root of 1 square plus 0 square plus 4 square, which is equal to square root of 17. And similarly, AR bar, the unit vector is equal to, so we need to find out at origin. So 0 minus 1 into AX bar plus y minus y, that is 0 into AY bar plus 0 minus 4 into AZ bar. So we know how to find out the unit vector along a particular direction. AZ bar divided by square root of 1 square plus 4 square, and this gives rise to minus AX bar minus 4 AZ bar divided by square root of 17. So if you find out the resultant here, EL bar is equal to, substitute the values here, lambda and R and AR bar. The logic is very simple, only thing is you have to pay a little attention in order to simplify such types of problems. So finally we get 360 divided by 17 into minus ax bar minus 4 az bar volts per meter. So we have calculated the electric field intensities due to the sheet of charge and also due to the line charge, and the resultant electric field intensity will be the addition of these two individual electric field intensities. So hence E bar is equal to S bar plus EL bar, and if you add these two electric field intensities together, we are going to get minus 113.09 AX bar plus 360 by 17 into minus AX bar minus 4 AZ bar. And if you simplify this, we are going to get E bar as equal to minus 134.17 AX bar minus 84.7 EZ bar volts per meter. This is the answer for the first question, that is the electric field intensity at the origin because of the two charges. One is sheet of charge, and another one is line charge. Next, let us find out the second question, electric field intensity direction at 4, 5, 6. So first of all, I am locating the two charges once again as we have done in the previous case. Here the objective is we have to find out the electric field intensity at the point, the given point 4, 5, 6, and in order to find out the direction of it, we need to find out the unit vector along the direction. So the objective here is we have to evaluate the unit vector along the direction the resultant electric field intensity. So again, the same that we have done in the previous case, here also we have to consider the electric field intensity due to the sheet of charge and also due to the line charge at point 4, 5 and 6. And once we find out the resultant electric field intensity, we have to evaluate the unit vector for that. That will give us the direction of the electric field intensity at that point P 4, 5, 6. So first let us find out the electric field intensity at 4, 5, 6 due to the sheet of charge. Okay, as we discussed previously, E bar is the unit vector direction. First let us find out ES bar at 4, 5, 6. So we continue the same that we have done earlier, that is rho s by 2 epsilon naught into AN bar. So here we get the AN bar as equal to plus AX bar because this will be directed away from the origin. Okay, so here rho s by 2 epsilon naught into AX bar, which gives the magnitude. Substitute the value of rho s here, which is given in the problem. We get 113.09 AX bar. This is the electric field intensity due to the sheet of charge at the point 4, 5, 6. Similarly, let us find out EL bar at 4, 5, 6. That is the electric field intensity due to the line charge at that point 4, 5, 6, which is equal to lambda by 2 pi epsilon naught into R into AR bar. Here the magnitude of R will be equal to square root of here the point will be 4 comma y comma 6. So 4 minus 1 whole square plus the y coordinate will be 0. Because the sheet of, the line charge is going to be in the x and z planes, and the y coordinate will not be applicable here. So square root of 4 minus 1 whole square plus 6 minus 4 whole square, which is going to give us square root of 13, 1, 3. And the magnitude of AR bar, this is R, the value of R we are going to get as square root of 13, and the magnitude of AR bar is equal to 3 into AX bar plus y minus y, which gives us 0 because y coordinate will not be there, into AY bar plus 2AZ bar divided by square root of 3 square plus 4 square, and this gives rise to a value of 3AX bar plus 2AZ bar divided by root of 13, and substitute R and AR bar in the formula. We get EL bar as equal to 360 divided by 13 into 3AX bar plus 2AZ bar. This is the electric field intensity at point 456 due to the line charge, and the total electric field intensity at that point is equal to 190 is the addition of the two electric field intensities, and add those two, we are going to get 196.07 AX bar plus 55.38 AZ bar volts per meter. And after evaluating this electric field intensity, we have to find out the unit vector along this of this particular electric field intensity in order to evaluate the direction. So let us find out the unit vector. Unit vector is given as E bar divided, the vector divided by magnitude of E bar. E bar divided by mag modulus of E bar, which is going to be equal to 196.07 AX bar plus 55.38 AZ bar divided by square root of 196.07 square plus 55.38 square. And if we simplify this, we are going to get 0.915 AX bar plus 0.272 AZ bar, and this will give us the direction of the electric field intensity at that particular point. Next, the last problem which is given to us is we need to find out the force per unit length on the line charge. So here, in order to simplify this, we have to find out the force per unit length of the, on the line charge due to the sheet of charge, and this will be equal to the actual charge per unit length, lambda multiplied by the electric field intensity due to the surface charge, lambda multiplied by E. So lambda is given as 20 nanocoulombs, that is 20 into 10 to the power of minus 9, and the electric field intensity due to the surface charge is minus 113 AX bar here, because we consider the unit vector towards the origin, hence it will be minus AX bar. And if we simplify this, we are going to get minus 2.25 into 10 to the power of minus 6 into AX bar newtons per meter. So this is how we have to simplify the problem. This concludes this session. So please watch my videos and subscribe to my channel in order to get more videos and more updates. The next session, I would like to deal one more problem related to this particular topic. Until then, bye. This is Shivabiram signing off.